In the unending silent theatre of the cosmos, a tapestry woven from 100 billion galaxies, our own small stage can feel profoundly lonely. We search the heavens for a reflection, for a hint of the familiar, in the sprawling, indifferent dark. We are pattern seekers, hunting for echoes of our own cosmic story, written in the light of alien suns. For millennia we gazed at the pinpricks of light, imagining worlds but knowing none. Now our instruments are extensions of our senses, reaching across light years to decipher the most delicate of cosmic whispers. And in this grand quest there is no greater prize than finding a mirror to our own home star, a solar twin. Imagine a star so alike our sun in age, temperature and composition that it could be its long-lost sibling, a celestial entity born from the same generation of stellar nurseries, forged from a nearly identical recipe of primordial gas and dust. This is not science fiction. Such stars exist. They are our control group in the grand experiment of planetary formation, anchors of familiarity in a sea of cosmic strangeness. One such luminary, catalogued with the unassuming designation HD 85426, resides nearly 160 light-years away, a journey that would take a modern spacecraft millennia to complete. Yet its light, a faithful courier travelling through the void, brings us a portrait of a star that is hauntingly recognizable. From this immense distance, it appears as just another point of light, indistinguishable in a field of countless others. But when we decode its spectral signature, the light splits into a rainbow barcode revealing its elemental secrets. We see the familiar fingerprints of hydrogen and helium, the traces of carbon and iron, all in proportions that sing a song of home. It is a G-type main sequence star, a stable middle-aged furnace, just like our own sun. HD 85426 offers us a tantalizing proposition. If the star is a twin, what about its family of orbiting worlds? Does a similar stellar blueprint lead to a similar planetary architecture? Could there be a distant echo of our own? Terrestrial planets, our own gas giants circling this solar doppelganger. For years, this stellar sibling was known to harbour a solitary confirmed companion. A world unlike any in our own solar system, a class of planet that seems to be one of the galaxy's most common yet is conspicuously absent from our neighbourhood. It is a sub-Neptune. This name, while descriptive, fails to capture the sheer alien nature of such an orb. To comprehend it, we must first deconstruct our own local expectations. Our solar system presents a tidy arrangement: small, dense, rocky worlds huddled close to the sun, and colossal gaseous giants relegated to the cold outer suburbs. There is a vast gap between the largest terrestrial planet Earth and the smallest gas giant Neptune. A sub-Neptune lives in that mysterious chasm. Picture a sphere significantly larger than Earth but markedly smaller than Neptune. Its nature is an enigma, a puzzle of planetary science. Is it a super-Earth with a colossal rocky core shrouded in an impossibly thick, crushing atmosphere? Or is it a mini-Neptune, a scaled-down gas giant with a less substantial core and a deep churning envelope of hydrogen and helium? Perhaps it is a water world, an entire planet composed of exotic forms of ice, and a global ocean hundreds of kilometers deep, heated from below and capped by a dense steam atmosphere. The sub-Neptune orbiting HD 85426 was a fascinating discovery in its own right, a testament to the universe's varied imagination. It was first detected not by sight, but by its gravitational whisper. Astronomers used the radial velocity method, a technique of exquisite sensitivity. They watched the parent star HD 85426 not for a transit but for a wobble. As this unseen planet dutifully circled its sun, its gravity ever so slightly tugged on the massive star. This pull caused the star to perform a minute rhythmic dance moving towards and away from us. This stellar motion is imperceptible to the eye, but it leaves a telltale signature in the starlight. The light waves are compressed as the star moves towards us, shifting to the blue end of the spectrum. They are stretched as it recedes, shifting towards the red. By measuring this infinitesimal Doppler shift over many months and years, scientists could infer the presence of a massive orbiting body. They could calculate its mass and the length of its year, painting the first strokes in the portrait of a new world. But this technique only reveals a planet's mass, not its size. To know that you need a little bit of luck, you need the planet's orbit to be perfectly aligned with our line of sight. You need it to pass directly in front of its star. You need a transit. The transit method is a concept of beautiful simplicity yet Herculean in its practical difficulty. Imagine standing miles away from a colossal lighthouse beacon on a perfectly dark night. Your task is to detect the moment a single tiny gnat flies across the face of that brilliant distant lamp. The dip in brightness would be almost immeasurably small, a fleeting flicker lost in the overwhelming glare. This is the challenge faced by astronomers. A planet passing in front of its star blocks a minuscule fraction of the light, typically less than 1%. For an Earth-sized world crossing a sun-like star, the dimming is closer to 1/100th of 1%. It is a shadow so faint it would be utterly invisible to any backyard telescope, lost in the shimmering of our own atmosphere. To hunt for these phantoms, we built observatories in space, robotic eyes like the Kepler and TESS missions, staring unblinkingly at vast patches of sky. They monitor the brightness of hundreds of thousands of stars with relentless, mind-boggling precision, and so astronomers turned their instruments towards HD 85426, hoping to catch the sub-Neptune in the act of crossing its sun. They knew its orbital period from the wobble data, so they knew exactly when to look. The observation was planned not as a mission of discovery but one of confirmation. The goal was to measure the dip in starlight, to determine the planet's physical size, to calculate its density, and to finally give substance to this gravitational ghost. The team gathered the data, began to stream in from a remote observatory, each data point a measurement of stellar flux. The light curve, a graph of brightness over time, started to form on their screens. It was a flat line representing the star's steady, unwavering output. Then, precisely as predicted by their orbital models, the line began to dip. A slow, graceful scoop appeared in the data as the sub-Neptune began its passage across the stellar disk. The transit had begun. There was a quiet satisfaction in the control room, the feeling of cosmic mechanics unfolding with the elegant predictability of a well-made clock. But the universe is rarely so simple. It is a clockmaker of infinite and sometimes mischievous subtlety. As the hours passed and the full transit was recorded, the researchers began their analysis. And that is when they first noticed it. The anomaly: the transit did not happen at the exact moment the models had forecast. The discrepancy was not large, a matter of mere minutes against an orbital journey lasting many days. To an outsider, it might seem like a rounding error, a trivial offset in the grand celestial dance. But in the realm of astrophysics, where orbits are governed by the unyielding laws of gravity, a deviation of minutes is a roar. It was a clue, a breadcrumb left on the cosmic trail, suggesting that the story of this system was more complex than they knew. The sub-Neptune was not alone in the dark. Something else was out there, an unseen presence, a hidden influence gravitationally nudging the known world. The surprise had arrived. The hunt was on. This phenomenon is known as transit timing variation, or TTV. It is one of the most powerful tools in the exoplanet hunter's arsenal, a method for finding worlds that may never transit at all. To understand it, let us imagine two children on adjacent swings at a playground. If one child is swinging alone, their rhythm is perfectly regular, a predictable arc back and forth. Now imagine a second child begins to swing nearby. Even if you can't see the second child, you might notice a change in the first. As their swings align, a tiny, almost imperceptible gravitational pull exists between them. When the second child is swinging forward as the first swings back, they are pulled slightly closer, subtly shortening the first child's arc. When they swing in unison, they might be pulled slightly apart, lengthening it. Over many cycles, the first child's swinging rhythm is no longer perfectly regular. It speeds up and slows down in a complex but repeating pattern. By meticulously measuring the variations in the first child's swing, a clever physicist could deduce the presence, the mass, and even the orbital period of the unseen second child. This is precisely what astronomers suspected was happening at HD 85426. The sub-Neptune was the first child on the swing, and its transit was its rhythmic passage. The fact that its transits were arriving a little early then a little late was a clear sign that it was being perturbed by a sibling. A new hypothesis was born from this single surprising observation. The system was not a lonely star and its solitary planet. It was a true solar system with multiple worlds locked in a complex gravitational embrace. The initial excitement gave way to the sobering reality of the work ahead. One anomalous transit was not proof. It was a tantalizing hint, but it could also be a fluke, an instrumental artifact, or a misinterpretation. Science demands rigor and reproducibility. The team needed more data, many more transits, to confirm the pattern of the variations. This required a coordinated campaign booking time on telescopes around the world, hoping for clear skies, and patiently waiting for the planet to perform its transit every time it completed an orbit. It was a slow, painstaking process. For months, which turned into years, they watched and recorded. Each new transit was a precious piece of the puzzle. Sometimes the planet would arrive ahead of schedule, other times it would be tardy. Slowly, meticulously, a distinct pattern began to emerge from the noise. The transit timing variations were not random, they were cyclical. The data traced a beautiful sine wave on their graphs, the signature of a persistent rhythmic gravitational tug. The invisible companion was real. From the amplitude and period of that wave, the scientists could begin to sketch a portrait of this hidden world. They calculated its probable mass and the characteristics of its orbit. The math suggested not one but two additional presences were required to explain the full complexity of the timing variations. The solo sub-Neptune was in fact the largest member of a trio. Two sneaky companions had been orbiting alongside it all, along their gravitational voices too faint to be heard with the radial velocity method, their bodies too small or their orbits too misaligned to produce their own obvious transits. They had remained hidden, their existence betrayed only by the subtle influence they exerted on their larger sibling. It was a stunning piece of celestial detective work, conjuring planets from the gravitational shadows. But the ultimate confirmation, the smoking gun, would be to actually catch one of these smaller worlds in transit. The team refined their models, predicting where and when these more diminutive bodies might cross the star. The chances were slim. The predicted transit depths were minuscule, bordering on the limits of detection. They were looking for a dip in starlight so slight it could easily be mistaken for instrumental jitter or a passing stellar flare. They focused their instruments once more on HD 85426's, this time staring intently at the star during the predicted transit window for one of the new candidates. The hours ticked by. The light curve remained stubbornly, disappointingly flat. Doubt began to creep in. Had they misinterpreted the data? Was the TTV signal a ghost in the machine? And then they saw it. A tiny, almost imperceptible notch in the data. It wasn't a grand scoop like the sub-Neptune's transit, but a shallow, timid dip. It was the shadow of a much smaller world, a super-Earth perhaps fleetingly passing before its distant sun. It lasted for only a short while, and then the starlight returned to its full, steady brilliance. The control room erupted. They had done it. They had found the first sneaky companion. The second soon followed its even more subtle transit, captured months later after another intense observation run. The family portrait of HD 85426 was complete. It was a star like our Sun, but its system was nothing like our own. Instead of a familiar layout of small inner worlds and large outer ones, HD 85426 hosted a compact configuration of 3 planets, all larger than Earth, all orbiting closer to their star than Venus does to our Sunday. The system's architecture was a revelation, providing a crucial new data point in the grand theory of how planetary systems are born and evolve. The 2 newfound companions were significantly less massive than the original sub-Neptune. They were likely super-Earth's worlds with solid surfaces, but masses several times that of our own planet. Such a planet would be a formidable place with a surface gravity so strong it would challenge human biology. Its atmosphere would likely be thick and heavy, a dense blanket creating a runaway greenhouse effect. But the most elegant feature of this newfound trio was not their individual characteristics, but their collective rhythm. They were locked in a state of near-orbital resonance. Orbital resonance is a celestial harmony, a state where orbiting bodies exert a regular periodic gravitational influence on each other, because their orbital periods are related by a ratio of small integers. Think of a parent pushing a child on a swing. To make the swing go higher, the parent doesn't push randomly. They apply force at a specific point in the arc, in resonance with the swing's natural frequency. A small, well-timed push, repeated over and over, can lead to a large effect. In the HD 85426 system, the planets were doing the same thing to each other. For every few orbits the inner planet completed, the middle planet might complete one. For every few of its orbits, the outer one would complete one. This regular alignment means they always give each other a gravitational nudge at the same points in their orbits. This synchronous dance stabilizes their arrangement, preventing them from colliding or being flung out of the system. It is a delicate, self-correcting ballet that can persist for billions of years. The existence of such a resonance is a profound clue about the system's past. Planets are not born in these perfect, resonant configurations. They are born in a chaotic, messy disk of gas and dust, swirling around a young star. They grow by accretion, sweeping up material in their path, their orbits jostled and perturbed by countless other planetesimals. The early stages of a solar system are a violent, chaotic demolition derby. A stable, resonant chain of planets suggests a much calmer history. It strongly implies that these worlds formed further out from their star, in the colder, less turbulent regions of the protoplanetary disk. Then over millions of years they began a slow, majestic inward journey, a process known as planetary migration. As they moved through the remaining gas in the disk, they were drawn closer and closer to their present-day orbits. During this grand procession they naturally fell into step with one another, capturing each other in these stable, resonant locks. The system we see today is a relic, a frozen snapshot of the final phase of that epic migration. This stands in stark contrast to the presumed history of our own solar system. Our inner rocky worlds likely formed more or less where they are today. Our gas giants, however, are thought to have undergone their own chaotic migration, a violent epoch called the Grand Tack, where Jupiter and Saturn moved inward and then back out. This rampage would have cleared out any planets that may have existed where these super-Earths now reside at HD 85426. The architecture of this distant solar twins family tells us that the story of our solar system is not the only one. It suggests that for a star almost identical to our own, a completely different sequence of events can unfold, leading to a planetary arrangement utterly alien to us. There is no single universal blueprint for making a solar system. The process is contingent, sensitive to the initial conditions of the disk, the precise timing of giant planet formation, and a healthy dose of cosmic chance. The discovery of these two clandestine worlds reshapes our understanding of the planetary census. It proves that systems that appear to have a single isolated planet may in fact be hiding a richer, more complex family. How many of the thousands of known exoplanets are not solitary travelers, but are merely the largest and most obvious members of a hidden retinue? The transit timing variation method has opened a new window, allowing us to perceive the unseen, to map the gravitational landscape of distant systems. Each new system catalogued, each new orbital architecture revealed, helps us place our own home in a broader cosmic context. We are learning that our solar system, with its wide-open spaces between planets and its stark division between rocky and gaseous worlds, might actually be the exception, not the rule. The galaxy may be teeming with compact systems like HD 85426, packed with planets in tight resonant orbits. And with this new perspective comes a cascade of profound questions. These three worlds at HD 85426 orbit well within the star's conventional habitable zone, the region where liquid water could potentially exist on a planet's surface. However, being a sub-Neptune or a super-Earth with a thick atmosphere makes the existence of surface water highly unlikely. The crushing pressures and searing temperatures would create conditions far too extreme for life as we know it. But what about their moons? While we have not yet detected any, it is plausible that these large planets could host substantial satellites. A large, rocky moon orbiting the outer sub-Neptune could potentially be a haven for life. It would be warmed by both the light from the solar twin star and the radiant heat and tidal forces of its parent planet. Such a moon would experience a spectacular sky dominated by the looming banded disk of its gas-enshrouded host world. The discovery of these two sneaky companions has suddenly multiplied the potential number of interesting environments in this one single system. The future of this research is incredibly bright. With the power of the James Webb Space Telescope, we are moving beyond simply detecting these worlds. We are now entering the era of characterization. When one of these planets transits its star, a tiny sliver of starlight filters through the very top of its atmosphere on its way to our telescopes. Within that light is a chemical fingerprint, an absorption spectrum that can tell us what the atmosphere is made of. Are we seeing the signatures of water vapor, methane, carbon dioxide? Could we one day detect the chemical imbalances that signify the presence of biology, biosignatures like oxygen and ozone? For the first time in human history, we have the splate-chemistry, technological capability to ask these questions of planets. Orbiting a star that is a near-perfect copy of our own, the system of HD 85426 has become a prime laboratory for comparative planetology. It is our control case, our what-if scenario. What if our solar system's formation had been less violent and more processional? The answer, it seems, is a compact family of worlds, huddled close to their parent, dancing in a quiet, resonant harmony. This journey of discovery, which began with the search for a simple reflection of our sun, has led us to something far more valuable. It has revealed a foreign yet elegant cosmic arrangement that challenges our assumptions. It began with a single known planet, a curious anomaly in our celestial neighborhood. It proceeded with a surprise, a subtle deviation in a clockwork orbit that hinted at a deeper complexity. And it culminated in a revelation, the unveiling of two hidden companions that had been whispering their presence gravitationally all along. HD 85426 is no longer just a solar twin. It is a lesson in cosmic humility. It teaches us that the universe is not only more strange than we imagine, but more strange than we can imagine. Its secrets are not always announced with the blast of a supernova or the majesty of a galactic collision. Sometimes they are revealed in a transit that is a few minutes late. Sometimes the most profound discoveries are the ones that sneak up on us, hiding in plain sight, waiting for us to look just a little bit closer. Out there, in the quiet darkness circling a familiar-looking star, an entirely unfamiliar family of worlds continues its billion-year dance, unaware of the distant observers who have at long last noticed their subtle, beautiful, surprising choreography. The search continues no longer just for mirrors, but for the full, staggering diversity of worlds the cosmos has to offer.